Welcome to my PSGM presentation. My topic today is data-driven zip load parameter tracking with variable elimination using synchrophasor data. Moving ahead, I talk about the motivation, challenges, and contributions in this work. Zip load model is commonly used to represent the load model voltage dependency of power system load. We do need sufficient changes in measurements to avoid ill conditioning while estimating the parameters. If we try to estimate non-existing parameters in zip load model when there are not sufficient changes in measurements, then that could lead to inaccuracy. This paper presents a load parameter estimation method using least squares and stepwise regression with variable elimination. Along with that, a confidence factor computation methodology is also proposed. In this work, we consider two scenarios for zip load parameter estimation. The first scenario is positive sensitivity scenario, where the zip load parameters are assumed to be constant, and in negative sensitivity scenario, we don't put any such constraint on zip parameters, and they are allowed to vary with time. So we estimate parameters for both these scenarios. Moving ahead, I talk about the parameter estimation algorithm. The first parameter estimation algorithm that we consider in this work is the least squares estimation algorithm, where we are estimating parameters for both positive and negative sensitivity scenarios. For positive sensitivity scenarios, we have to estimate three parameters, which are Z, I, and P, the constant impedance, the constant current, and the constant power part of the load. In case of negative sensitivity, we have to estimate six parameters where we have the constant Z, I, and P parameters, and also the varying parts of these parameters. We estimate parameters using stepwise linear regression as well. In case of stepwise regression, we can either consider forward or backward elimination to estimate the parameters while doing variable elimination. In this study, we are using cumulative error to perform forward stepwise regression, and we consider parameter estimation for both positive and negative sensitivity scenarios using stepwise regression as well. For both these methods, we have also proposed a confidence factor computation methodology in this work. This slide presents the flowchart for parameter estimation algorithm. In our parameter estimation algorithm, once we have the moving window length and PMU reporting rate as input, we fetch the parameter estimation data, and after data cleaning, we compute the sensitivity, and if the sensitivity is positive, we use the positive sensitivity model for parameter estimation, and if the sensitivity is negative, we use the negative sensitivity model for parameter estimation, and we estimate parameters using stepwise linear regression and also the least squares regression. And once we have estimated parameters, we compute the confidence factor using a fuzzy based method where we have two membership functions and a fuzzy rule base to compute the confidence factors. Moving ahead, in this slide, I present some of the results for both positive and negative sensitivity scenarios. For positive sensitivity scenarios, the first scenario that I report has all parameters present. That means that all Z, I, and P parameters are present. And in this case, we have around 7.145% deviation in voltage measurements. And because of that enough deviation, we are able to estimate parameters correctly with both these estimation methods. And that is observed in the confidence factors as well. Whereas for the second scenario, we have a little bit less deviation, which in this case, because P parameter is missing, we are still able to estimate parameters quite accurately with both the methods. For the second scenario, that is negative sensitivity, in the first reported case, we have the constant power part as the varying part, and in this case, we are estimating six parameters using stepwise regression and the least squares regression. And again, because there is enough voltage deviation available, we are able to estimate parameters quite accurately using both these methods, which is confirmed by the confidence factors as well. Whereas for the second scenario, where we have constant impedance part as varying and we have slightly less voltage deviation, and because we are estimating a number of parameters, that is six parameters, our least squares based parameter estimation provides inaccurate estimates, whereas our stepwise regression provides accurate estimation because of variable elimination, and that is confirmed by the confidence factors as well. Moving ahead, I summarize the conclusion and future works. Based on our case studies, we observe that load parameter estimation is highly dependent on measurement deviation in the estimation window. When there is not enough deviation available, then the best estimation can only be achieved by eliminating the unnecessary variables. The confidence factor methodology developed in this work can give good insight into the accuracy of estimated parameters. Our future work is concerned with development of computationally efficient method for eliminating variables and also using machine learning for zip load parameter estimation. Thank you everyone for listening.